Hello, today we're going to talk about if events are independent or not and how to prove it algebraically or using math. So we already have talked a little bit about events being independent. We talked about a coin and a die. This is a great example of two events that are independent because if you know what happens on a coin flip, it should not influence the probability of getting a number, say a 5, rolled on a die. So knowledge of the one event occurring should not impact the knowledge of the probability of the second event occurring. Now, this brings us to this formula or rule, which is always true for independent events. Let's say we know that event A has already occurred. If two events are independent, this means the probability of event B should remain the same even though we were told that event A has already occurred. So this is saying the probability of event B occurring will be the same even though we know that event A has already occurred. So probably event B occurring is not impacted by the knowledge that event A has already occurred. So I'm telling you event A given has already occurred and you're like, it doesn't matter. Event B remains the same. The probability of event B will remain unchanged even though you're telling me that event A has already occurred. That is the concept of this rule. Similarly, if I tell you that event B has already occurred, you're like, doesn't matter. The probability of event A will remain unchanged even though I'm telling you that event B has occurred. So quick example on the side here. Let's say I want to know the probability of getting heads on a coin flip. Given that I rolled a 5 on a die, you should say, well, I told you that I rolled a 5 on a die. Well, it doesn't matter. The probability of getting heads on the coin flip will still be the same even though I told you that I rolled a 5 on a die. The probability of event A, heads, will remain the same, which is what this is saying. Okay, so now this rule is one of the rules that we know will prove independence. Another rule that we can derive is from the general multiplication rule. The general multiplication rule says the probability of event A and B is equal to the probability of A times the probability of event B happening given event A has already occurred. Well, if two events are independent, then the probability of event B happening given A already occurred will equal the probability of just event B. So basically, if that's the case, then we have a new rule here, which is the probability of A and B is equal to the probability of A times the probability of B. Meaning, even though we told you that event A has already occurred, you say it doesn't matter. The probability of event B remains unchanged. So here is our second rule for independence. It is the probability of A times the probability of B equals the probability of A and B. So only if events are independent is this true. Otherwise, that event B will be changed by A. So now we have two rules here for you for independence. They are the ones above here. The probability of A given B equals the probability of A. That's the conditional rule, which I think actually makes more sense logically. Knowing event B has occurred, it won't influence A. And then the other one is the multiplication rule for independent events. The probability of A times the probability of B equals probability of A and B. This one I have a feeling you guys use more in Algebra 2 because it's easier to memorize. Now these rules are only applicable if the events are independent. So I want to mention that. Now here is a question that was from Algebra 2. And you may have recognized it because we used it in Algebra 2. Sean's team has a baseball game tomorrow. Sean pitches 50% of the games. So the first thing I'm going to do is I'm going to write the probability of Sean pitching is 50% or 0.5. Now there is a 40% chance that it's going to rain tomorrow. So the probability of rain is 40% or 0.4. Now, it says if the probability that it rains given that Sean pitches is 0.4, so the probability it rains given Sean pitches, so slash given Sean pitches is 0.4 or 40%, then these events are. Okay, so just logically, do you think that Sean pitching, if I tell you Sean's pitching, that's going to influence the probability of rain? I'm hoping you're saying no, it shouldn't, right? Well, it actually is true based on the independence rule from above. The first rule says the probability of A given B should equal the probability of A. Given Sean pitches, it should not influence the probability of rain, okay? So the probability of it rain given Sean pitches should just equal the probability of it just raining in general. Doesn't matter if we tell you that Sean pitches, doesn't matter if anyone pitches. The probability of rain should just be the probability of rain. The probability of rain is 40%, which they told us here. The probability of it raining given Sean pitches is still 40%, which they told us here. So because the probability of it raining given Sean pitches equals the probability of it just raining alone, these events are independent. We know that Sean pitching will not influence if it rains or not. Now, are the events mutually exclusive, you ask? Well, if two events can happen at the same time, they are mutually exclusive. So let me ask you, can it rain and can Sean also pitch? And if the answer is yes, which I think so, yes, then they are not mutually exclusive because it can rain and Sean can still pitch. Okay, now I want you to look at this one. Question number 2 has this two-way table, and we're going to talk about the difference between mutually exclusive and independent. So let's list two events that are mutually exclusive. Before I go over it, I want you to stop the video here and ask yourself, what are two events that are mutually exclusive? We went over this before. So I'm hoping that you said something like Ford or Chevy. Ford or Chevy. Those are mutually exclusive because if you're Ford, you're not a Chevy. If you're Chevy, you're not a Ford. They do not intersect. So I told you guys, if you pick anything that is parallel, two events that are parallel, those are going to be mutually exclusive because there is no intersection, okay? So you could have picked Ford and Chevy, Ford and Dodge. You could have picked anything that did not intersect. You could also have picked yes and no. Yes, four-wheel drive, or no. Those don't intersect as well. So either two from the row or two from columns. They don't intersect. Two events that are complements. So complements means that they add up to one, or one whole, or 100%. So can you think about two events up here that are complements? Stop the video here and write something down. Okay, I'm hoping you said something like yes, four-wheel drive, and no, four-wheel drive. Those two will add up to the total, which is 125. You could also have said something like Ford and not Ford. The opposite of Ford is not Ford, okay? So anything that is an event and the complement would be not Ford. So that would be probability of Ford complement. Those are considered complements. Okay, now let's get into independence again. Here we go. C, what's the probability that they drive a Chevy? All right, so write that one down. Write down the probability of Chevy, please. Stop the video here and write it down. Okay, so I'm hoping for the Chevy you wrote 50 over 125. Chevy total is 50 over 125. So that's that one. Okay. Now it says, what is the probability that a randomly selected truck owner from the group drives a Chevy given that they have four-wheel drive? Okay. So first step is let's write the notation. Probability they drive a Chevy given that they have four-wheel drive. All right. So find this now. Stop the video and do this. Okay, so for this one, I'm hoping you went to the yes, which is four-wheel drive, and out of the four-wheel drive, which is 80, there's 32 Chevys out of 80. So it was 32 out of 80. the total four-wheel drive restricts the denominator, and this is Chevy and four-wheel drive. Now, the next part is the last part. The culmination is, are the events drive a Chevy and four-wheel drive independent? Okay, so if you look above at parts C and D, C says the probability of Chevy. D says the probability of Chevy given it has four-wheel drive. So this lends itself very nicely to probability rule number one, which is the one that says probability of A given B equals the probability of just A. Because you have Chevy given four-wheel drive, so all you have to do is see if they're equal or not. If they're equal, they're independent. If these two are not equal, they're not independent. That's it. So yes, could you do this other rule, the AND rule, which is the probability of A times probability of B equals probability of A and B? You could, but why would you when you already have the probability of Chevy, probability of A, we'll call this event A, okay? Probability of Chevy given four-wheel drive, A given B. So all you have to do is see if these two things are equal and you're done. Okay, so I'm going to write down the rule first in general, okay? The rule says the probability of A given B is equal to just the probability of A, okay? If these are equal, the events are independent, okay? So I'm going to let event A from above be Chevy. So is the probability of Chevy given, let's let event B be four-wheel drive, equal to just the probability of event A. Event A, we said we defined it as Chevy, okay? Probability of just Chevy. All right, so now we're going to write down our answers. This is the answer. This is the answer to part D above. This is the answer to part C above, okay? So part D above was 32 over 80. Divide that and see what decimal it equals. And part C was this one, 50 over 125. So divide that and see what decimal it equals and write it down. And if they're equal, they're independent. So I ended up getting 0.4 or 40%, and I got 50 over 125 equals 0.4. So yes, they are equal, meaning the probability of getting a Chevy is equal to the probability of getting a Chevy, knowing that the vehicle had four-wheel drive. Because they're equal, yes, the two events are independent. And that's how you prove independence in statistics. You don't actually have to do anything except show that these two statements are equal. But I like if you show the notation like I did above here. So specifically this notation here that I'm pointing to in this box here, this is really nice, showing both sides are equal. Okay, so that's it for this quick video. I just wanted to mention that usually on the AP we've seen that they've done something like this where they'll lead you into it really nicely because they'll ask you for a part C, they'll ask you for a part D, and then they'll ask you if the two events are independent. So all you have to do is show that C and D are equal, they're independent, or C and D are not equal, they're not independent, and you're done. All right, thanks for listening.